good afternoon, good morning, good evening, all you. So today we are here to attend the talk that will be done by Dr. Lilas Alrahis. And we have also the pleasure here to have Professor Hussam Amrouche from University of Stuttgart that will be the session chair today. So thank you very much for accepting our invitation, Hussam and Lilas. So now I can give the floor to Professor Hussam to do the presentation of Lilas. No?
Thanks a lot, Ricardo, and thanks for organizing those series of events. I do believe many people really benefiting from all those invited talks. Today, it's my pleasure to introduce Lilas Alrahis. She received her master and PhD degrees in the Electrical and Computer Engineering Department from Khalifa University, United Arab Emirates in 2016 and 2021, respectively. Now, she's currently a postdoctoral researcher with the Design for Excellence Lab, headed by Professor Oscar Sinan-Uglo in the Division of Engineering at the New York University, Abu Dhabi. Her current research interests include hardware security, design for trust, logic locking, applied machine learning, and in general, of course, digital logic design. She's currently serving as associate editor of the Integrations, the VLSI journal. She's also a reviewer in many top journals, including IEEE Transactions on Information and Security, IEEE Access, IEEE Embedded System Letters, and others. Interestingly, she won the MWS CASS Best Paper Award in 2016 and the Best Paper Award at the Applied Research Competition held in conjunction with the Cybersecurity Awareness Week in 2019 and again 2021. So it's a great pleasure to have her, and she will be telling us today about the graph neural networks for hardware security. We know that graph neural network GNNs is an extraordinarily important topic nowadays, and if we combine that with hardware security, which is another important topic, definitely this talk will be very interesting for many researchers. Okay, so great pleasure. So Lilas, please go ahead.
Thank you very much for the introduction. I'm very excited to be presenting here today. Before I start the presentation, I would like to thank Professor Rees for the invite, Professor Hussam for initiating this, Dr. Guilherme for organizing this talk. Apologies for my hoarse voice. Today is really not the time for me to lose my voice. I would like to thank the audience for attending and joining this session today. Today, I'm going to show you how we use graph neural networks for hardware security. This is the outline of the talk. First, I will discuss machine learning on circuits, how we can perform it, specifically using graph neural networks. And then I'm going to discuss how we use GNNs for hardware security. Before we discuss our contributions, I will motivate why we are interested in hardware security. And then discuss our contributions and finally move to the conclusions. So machine learning has become an increasingly powerful tool for solving complex problems, for example, object recognition, speech recognition, and to no surprise, machine learning has beaten state-of-the-art on many circuit-related problems. For example, Google developed a learning-based approach to chip placement in order to optimize for performance, area, and power. Also, machine learning can be used in hardware security, for example, to detect some hardware trojans, which are some malicious modifications in the circuit. Now, to run machine learning on a circuit, one would need to take the circuit. In this example, I'm showing a gate-level representation, but it could be the RTL representation of the circuit, it could be the layout representation, and one would need to encode it in vector form, which is expected by the machine learning model, which will perform some desired task. In this example here, I am showing a classification task, but of course, we can solve other tasks like regression. So the way we started to use graph neural networks on circuit was that we had some interesting circuit-related task, which we thought that machine learning will be useful to solve it. And then we started to think, how can we encode this complex circuit into a fixed size vector form? How can we do this transformation automatically by automatically extracting the features of the circuit? So One observation that helped us, which is a simple observation, is that circuits are graphs. So the graph is the natural representation of a circuit. As you can see in the example here, on the left we have a gate level netlist, and you can see how it is nicely captured as a graph on the right. In this example, we are representing each gate in the netlist as a node. We're also representing the inputs of the circuit as nodes as well. The connections in the graph represent the wires in the circuit. Now, if we initialize this graph and we initialize each node in it with some feature vector that captures, let's say, the type, the Boolean functionality each node is performing, then we are able to fully capture this circuit as a graph. So, based on this observation, we start to think, okay, how can we take advantage of this graph representation? How can we take advantage of this relational structure for better prediction? And that's why we started to look at graph representation learning. Now, to perform machine learning on a graph, it is a more complex task than performing machine learning on structured data like images, like grids. So here on the left, you can see a graph, and on the right, you can see a grid. First, a graph can have an arbitrary size. So if we're dealing with a data set of graphs, each graph can have a different size. It can have different number of nodes, different number of connections, unlike images where you have, or a grid where you have a fixed size. Also, in a graph, there's no spatial locality like grids. So here on the example here on the grid, we're able to pinpoint where is pixel 00. We can also pinpoint where is pixel 44. We're also able to extract the spatial locality. So we know what is on the right of this pixel. We know what is on the left of this pixel. However, in a graph, there is no spatial locality. We don't know what is the right to a node. We don't know what is the left. And also, there's no fixed gate or node ordering or reference point. So for example, here, where is node 00? Where do we start from? In addition, each node can be connected to a different number of nodes in the graph. So one node maybe is connected to 5 nodes in the graph, while another node is connected to a single one. So the size of the neighborhood here is not fixed. So in order to perform machine learning on a graph, what is needed is that one would take this raw data, which is the graph, and then perform some feature engineering to extract properties of the graph and then represented in structured format, which will be passed to the machine learning model. Now, graph representation learning will eliminate this feature engineering step, and it will automatically learn and extract these features from the graph and then pass the extracted structured data to the machine learning model. So basically, graph representation learning will take this given graph and will generate an embedding vector for each node in the graph that will capture its properties. And it will also capture the properties of the neighborhood of this node and the connectivity of the graph. So graph representation learning has many applications. It is used in chemistry to analyze protein-protein interaction graphs. It is heavily used in social networks and, of course, many other applications. And we started to use it for circuits. So one way to do this graph representation learning is to apply neural network on graph data, and this is what we call graph neural networks. In a graph neural network, given this graph, to generate this embedding vector for a given node, let's say the node colored in orange here, this node will receive information from its direct neighbors. So by information here, we mean we start by having a graph in which we have an initial feature vector that captures the properties of each node in the graph. So what happens is here, this node will receive these features of its neighbors, and it will aggregate them, combine them in a way with its own features, and update its feature vector and generate a new embedding. Each one of its neighbors also collects information from their own neighbors. And so by doing this for multiple number of layers, we will generate an embedding vector for each node in the graph that captures the properties of the node itself, captures the properties of its neighborhood, and also the connectivity in the graph. So this is a very important feature, that the extracted vectors are mindful to each node's neighborhood. So that's why we have decided to use graph neural networks to learn on circuit. If we take a circuit, we can represent it as a graph, as I have showed earlier, and then we can pass it to a GNN, in which we can start to ask and answer some interesting questions. For example, we can check if the circuit contains a hardware Trojan, which is some malicious modification. So now that we are a bit more familiar with the concept of a GNN in graph representation learning, I'm going to move to hardware security to discuss why it is important to secure the hardware, and then I'm going to discuss our GNN for hardware security applications. So, the semiconductor industry prior to the 80s used to follow a vertical integration model where leading edge design houses used to design, manufacture, and test their own products. So, they had complete control over the IC supply chain. However, with the dramatic increase in IC's fabrication cost due to technology shrinking, the companies had to let go of fabrication. So, for example, here you can see that building and equipping a 5 nanometer plant now runs about $5.4 billion, more than 3 times what was required for the 10 nanometer plant. So now the semiconductor industry follows a horizontal integration model where leading edge design houses such as AMD outsource fabrication to companies like TSMC and testing to companies like ASE. Now, the concern is that the companies that perform fabrication, testing, and so on are located across the globe, as you can see here. So there's no control on the design process, and the levels of trust go lower as the design go down the supply chain. And several hardware-based attacks exist in this globalized supply chain, which include counterfeiting, IP piracy, overbuilding, hardware Trojan insertion, and reverse engineering. So, counterfeiting deals with recycled, out of spec chips that are made to appear identical to the genuine IC. And IP piracy, it means stealing the device. Sorry, the light here is just going. Yeah. I just had to move to have the light turn on again. Yeah, IP piracy means stealing the design to build competing devices without incurring the research and development costs. And overbuilding is another form of piracy in which an untrusted foundry can produce extra chips and sell those illegally. Hardware Trojan means performing some malicious modification to the circuit to steal some secret assets on the chip or to change its functionality or to reduce its reliability. Reverse engineering means to extract the design details, and this can be an enabler for all of these hardware-based attacks that I have discussed. So in my work, I mainly focus on the IP piracy and overbuilding threats. And to show you an example that these threats are real, AMD released that it suffered from graphics IP theft in 2020. So all of these hardware-based attacks may cause financial harm to the design companies, but they also introduce risk to end users due to the loss of reliability and security. So how can we regain trust? To answer this question, we need to list the untrusted entities in the supply chain, which includes the foundry, the assembly and test companies, and the end users. And there are different design for trust techniques that can be implemented to protect the design under a specific threat model. For example, to prevent specifically IP piracy and overbuilding. For example, split manufacturing can protect the design from an untrusted fab, but it cannot protect it from assembly and test and the end users. IC camouflaging can protect the design only from the end user. However, logic locking is considered a holistic solution that can protect the design throughout the supply chain. And this is why in my work, I mainly focus on logic locking. So, how to regain trust in the IC supply chain? One holistic solution is logic locking. So what is logic locking? Logic locking hides the functionality of the design by inserting key gates that are controlled by newly added key inputs. So here I am showing you an example of traditional logic locking. On the left here, you can see an original netlist, and on the right, you can see the locked version. We are locking it using 3 key gates that are highlighted in green, which are controlled by newly added key inputs. So the correct key here happens to be 100. This original netlist, if we give it an input pattern of all zeros, it's going to give us this output of 0. And this locked circuit, as long as we have this correct key, we're going to get the correct response. However, if we have an incorrect key in place, we are going to get an incorrect response. So that's why logic locking can thwart piracy and illegal overproduction, because even if the adversary can see the locked netlist, they will not be able to activate the functionality without knowing the secret key, which is the designer's secret. So this locked netlist without information regarding the key will be passed to the untrusted stages in the supply chain like fabrication and testing. And then the chips that pass the test will be activated by the IP owner by loading the secret key onto a secure memory on the chip. Now, there are many ways to implement logic locking, and researchers have developed multiple attacks to evaluate the security promises of logic locking. And before we discuss some of the attacks, it is important to identify the capabilities of the attacker. So, in logic locking, we typically consider two types of threat models. The first threat model is what we call an oracle guided threat model, in which we assume we have a very powerful attacker. This attacker has access to the reverse engineered locked netlist. And this can be obtained by reverse engineering either the layout information during fabrication or by reverse engineering the chip, which can be purchased from the market. This attacker also uses the chip as an oracle. This chip contains the secret key. The attacker cannot see the key, but the attacker can give this chip some input patterns and observe the correct output responses. So here the attacker, by looking at the structure of the locked netlist with the key logic, the attacker can identify some meaningful input patterns that will be applied to the chip, and based on the responses, the attacker can decipher the secret key, which happens to be 100. So it's a binary key here. So some examples are the sensitization and the famous SAT-based attack. Now, another threat model is the oracle-less threat model, in which the attacker does not have access to this functional chip. The attacker only has access to the reverse engineered locked netlist, and based on the structure of this netlist, the attacker will identify the key logic and isolate it, and either from the structure infer the key, the secret key, or remove the protection logic completely. And this is considered a more powerful attack because the attacker can break logic locking with limited resources, which means that the attacker can also launch the attack earlier in the supply chain. So to visualize this, here I'm just showing you the flow from fabrication to deployment. And if we are going to run an Oracle-guided attack, we will need to wait until the chip is sold in the market. We can obtain this chip, reverse engineer it, perform some analysis. So we will need a number of chips, one that we will reverse engineer and another one that we're going to use as an Oracle. And then we will be able to recover the original design. However, if we want to launch an Oracle-less attack, we can launch it earlier in the supply chain. We can launch it during fabrication, in which we can reverse engineer the layout information, obtain the locked netlist, perform some structural analysis, and recover the original design. So in my work, I mainly focus on these Oracle-less attacks on logic locking. Now, one of the first Oracle-less attacks on logic locking happened to be a machine learning-based one. It is called the SAIL attack. And the SAIL attack exposed a vulnerability in logic locking. Now, when we're implementing traditional logic locking, usually there is a mapping between the added key gate and the correct key value. So here, this is an example of an original design, which we wish to lock. And here we locked it by adding a key gate. And this key gate, the one that is added now, is an XNOR. Now, because logic locking is supposed to maintain the correct functionality when you have the correct key in place, this means that this XNOR gate should translate into a wire after adding the correct key, which means that the correct key must be 1. So now, an attacker knowing this information can figure out the correct key by looking just at the structure of the locked design. So in order to break this mapping, what we usually do is we perform a resynthesis stage in which we hope the synthesis tool will perform some optimization for us so that it will transform this key gate and along with some other local transformations. So this is basically some form of bubble pushing for us. So in this example, you can see that the XNOR key gate translated into XOR gate along with some other translations. However, the correct key still remains to be still remains to be 1. Now, the sale attack, what it does is it takes this resynthesized netlist, encode it, pass it to a machine learning model, and undo synthesis to recover this locked netlist prior to synthesis. And then the attacker can perform key guessing and figure out the correct key. So SAIL showed that traditional logic locking is vulnerable to machine learning-based attacks. However, SAIL requires some feature engineering. So it performs some feature engineering to encode the circuit into a form which is expected by the machine learning model. So this motivated us to work on machine learning on circuits. And since it was using feature engineering, we started to think, okay, can we use GNNs to do this automatic encoding for us and solve more complex tasks? So now I'm going to discuss our GNN base attacks that we have developed on logic locking, and also our GNN for functional reverse engineering platform. So this is something I have showed earlier. I have shown you that using a graph neural network, we will be able to generate an embedding for each node based on its neighborhood. However, how this is really done? So what are the functions that are used here? First, there are many different ways to do this, and there are many different GNN architectures. One will need first to aggregate the information obtained from the neighbors, so it will need to combine it in a way. And then the aggregated information needs to be combined with the initial features of the target node itself. So in order to do this, there is just one restriction, which is that in the graph, the ordering of the node does not matter, which means that whatever function we're going to use here to aggregate the information should be order invariant. For example, we can do averaging. Averaging is order invariant. We can do summing, which is order invariant. We can use a max function, which is again is order invariant. And we can combine this with the information of the target node by either concatenation, summation, or any other operation. So now I'm just going to show you one basic GNN model. Again, the GNN can be implemented in many ways, but this is just one basic model that performs averaging. So for the notation, we assume we have a graph G with a node set V, and we have X, which is the initial matrix of node features. Small letter v is a node in this graph, and n of v is the set of neighbors, which are the direct neighbors of node v. Now, we need to generate an embedding, which we refer to as H, and the initial embedding for node v, so at layer 0, is initialized with the feature vector of node v. So we start with these feature vectors, and then we start to do the aggregation. Z of v is the final node embedding, which we are expected that the GNN will be generating, and this will be taken from the embedding obtained at the last layer of neighborhood aggregation. So here we're showing you in an equation how this is computed. So in order to compute the next embedding for node v, what we do is we perform, in this example, an averaging. So you can see that we consider each node u in the neighborhood of node v, and then we look at the embedding, the current embedding of node u, and then we do an averaging by summing these embeddings and dividing by the number of neighbors of node v. You can see here that we have a nonlinear activation function. We have this averaging that I have just discussed, and we have some linear transformation layers. You can see that in addition to this averaging of the neighbors, we also have the current embedding of the target node itself, which will be passed with some, it will go through some linear transformation. Again, the averaged information will also pass through some linear transformation. They're going to be combined. In this example, they are added. And we do this for a number of layers until we reach this final embedding that is going to be used further for the classification task. So in summary, we take the graph, we have the initial feature matrix, we feed both the graph and the feature matrix to the GNN. The GNN will be generating this H embedding matrix, which will be passed to this classification stage. In this example, I'm showing classification. And mostly in our work, we focus on classification. As I mentioned in the beginning, we can solve other tasks like regression, but everything you're going to be seeing today is related to classification. Now, even for classification, we can perform classification at different levels. So either we do classification at the node level. So by getting this vector for the node, we can classify the node based on these properties we have extracted. We can also perform the classification at the graph level. So by combining all of the vectors we have obtained for all the nodes in the graph and combine them into a single vector and use that for classification, we can infer some information about the graph. And we can also perform it at the link level. So we can perform, for example, link prediction. And by that, we would need, if we're considering this link here, we will need to consider the embeddings generated for the nodes at its both ends. So in our work, we have used these different classification levels to solve different hardware security related tasks, which I am going to discuss next. So in summary, we can perform classification at the link level, we can perform it at the node level or the graph level. So now I'm going to start by discussing our applications in which we used node level classification. So the first application we have implemented is GNN Unlock. This is a GNN-based Oracle-less attack on logic locking, specifically a type of logic locking that is called provably secure logic locking. Like I have mentioned earlier, logic locking can be implemented in several ways, and one way is this PCLL. The way this is implemented, we will take the original circuit, we will inject some built-in errors into the circuit to generate this modified circuit, and we will also add a restore circuitry. This restore circuitry will take the secret key as an input, and then it will check. If we have the correct key, the secret key in place, it will cancel these injected errors, and we will get the correct output. So now an attacker can trace the key inputs by tracing the secure memory on the chip and see where these key inputs are connected to. An attacker can then isolate and remove this restore circuit because you can see it is just connected via one point to the circuit. However, if the attacker removes the restore circuit, they are not going to end up with the original circuit. They will end up with a modified circuit, which is not what the attacker desires. So we take a closer look onto how this modification is implemented. In order to inject the errors, a perturb unit is added. This perturb unit will inject the errors for some specific input patterns. So which means now if an attacker can identify the restore unit, the perturb unit, the attacker will end up having this original circuit. So one thing is that these restore and perturb blocks, they have specific functionality. They're Hamming distance checkers in this case. So they have a specific functionality and they have some specific characteristics. And what we wanted to do is we wanted to represent this circuit as a graph, and based on the structural information that we can extract from this graph, figure out which nodes belong to the restore block, which nodes belong to the perturb block, and which ones belong to the original circuit. So basically, we will get an output like this. By representing the circuit as a graph and passing it to the graph neural network, we will be able to identify where's the perturb, the restore, and the original design. Now that you're looking at the solution, you might think that this looks like an easy problem. But just to show you that this is easy because we use the GNN, what I am showing you here is that once we extract the circuit and we extract some feature vectors for the gates in the circuit, we use TSNE to visualize these features. So these are the features that are going to be passed to the GNN. So what you can see is that it is straightforward to identify the restore unit, which is colored in red, but it's difficult to identify the perturb unit. As you can see, it's difficult to separate the blue nodes. However, when we feed these feature vectors along with the graph, the structure of the circuit, to the GNN, the GNN will automatically generate an embedding for us. And now I am visualizing the embedding obtained by the GNN. So you can see the GNN now give us a new embedding in which similar nodes are close together in the embedding space, which means that the restore nodes are close together, the perturb nodes are close together, and then the original design can be isolated. So this is the high-level idea of GNN Unlock. To implement it, we have a training phase in which we have a set of benchmark circuits to train the GNN on. So we use those to build a data set, and this data set of circuits will be converted to graphs using our own netlist to graph transformation and feature extraction. And then we build a training set, train the GNN. Once we obtain the trained GNN model, we can launch the attack. So we take, during the attack stage, an under-attack PCLL netlist, which the model did not see before. The attack will convert it to a graph, perform some feature extraction, pass it to the trained GNN. The GNN will give us some predictions regarding the nodes, which will be passed to a post-processing stage. And finally, we are able to identify exactly which nodes, basically which gates, are part of the original circuit. So now I'm going to discuss these these 3 steps in detail. So for the dataset generation, what we do is in GNN Unlock, we consider different types of PCLL locking schemes like anti-SAT, TT-lock, SFLL HD. These are just some representative examples, but if you check our paper, you will see that we considered even more locking schemes. So we also take some benchmark circuits that we are going to lock. So we consider the ITC99, SCASS 85 circuits. We take them at the RTL level, and then we lock them. So when we lock them, when we implement the locking, we implement the locking using different key sizes and using different parameters for these locking schemes. And after doing the locking at RTL, we perform synthesis. When we perform synthesis, we also consider different technology libraries just to check if our attack is generic or not. Can it handle different technology libraries? So we consider 45 nanometer, 65 nanometer. And then after we get these synthesized netlist, we perform some dataset split so that we train the GNN. Now, assuming I want to attack this B14 benchmark from ITC99, we lock it, as I mentioned, using these different locking schemes, using different key sizes. So we will generate more than one trial, a locked version of this B14. And then we train, you see the training set is highlighted in green, on the rest of the benchmarks in the ITC benchmark suite. And then we can also take one circuit out for validation. So the circuit, the one we are attacking, is never seen during training. So we do this, we always leave one circuit out when we are performing the evaluation of our attack. So we talked how we do this locking. We generate a set of circuits. Now we need to convert them to graphs. So this is an example of how we do this netlist to graph transformation. Here you can see a netlist, and this is the graph representation. Typically in our work, we represent the netlist as a non-directed graph. We represent each gate in the circuit as a node in the graph. In some of our applications, we do not represent the primary inputs or the primary outputs. This is because in this specific case of GNN Unlock, we are interested in classifying the gates, which gates belong to which unit in the design. So that's why we only represent the gates as nodes, but we also keep the information whether a gate is connected to a primary input or not in the extracted feature vector. Also, what does it mean when we say an undirected graph? By undirected, we just mean that when we do this neighborhood aggregation, when we are collecting the information from the neighbors, we collect information from both the inputs and the output of the gate. So that's why it feels like there's no more direction, because we're not separating the input from the output, but we're considering all the direct connections as neighbors. So now I'm showing you an example of the feature vector. Like I mentioned, we get a graph, and we also initialize each node with a feature vector. And this is the feature vector we are using. First, we have a set the first few elements to identify if the gate is connected to a primary input, a key input, or a primary output. So this specific example is for node G, gate G. It is connected to a primary output, so you can see one in the entry for the PO. And we also captured the Boolean functionalities in the neighborhood of this gate. So we check the inputs and the outputs of this gate. We check what is the type of Boolean functionality that exists, and we also count the number. So in this example, we can see that in this neighborhood of G, we have 3 XOR gates, and we also have a single XNOR gate, which is nodes G on functionality. I am putting here dots to tell you that, of course, we don't only consider XOR, XNOR, we consider all the possible Boolean functionalities in the technology library. So the length of this feature vector will depend on how many different Boolean functionalities we're expected to have in our circuit. We also encode the input degree and the output degree of the node. So basically the number of inputs and the number of outputs. So here this gate has 3 inputs and 1 output. Now, after we extract this feature vector, we also associate a label with each node. This label specifies whether this node belongs to the restore block, to the perturb block, or to the original design. And then we pass this information to the GNN. So here, again, I'm showing you the full flow. We take this reverse engineered netlist, the one we want to identify the perturb, restore, and original blocks. We convert it and represent it as a graph. Here I am showing you a graph colored in gray because we don't know the labels. We don't know which nodes belong to what block. But we extract some feature vectors, and then we pass it to our trained GNN model. The trained GNN model will color the graph for us. Basically, it will tell us the part or the logic each node belongs to. And just to show you the performance of the GNN on its own, it performs extremely well. As you can see, I'm reporting the accuracy, precision, recall, F1 score, and it's always around 99%. So it is almost perfect. What we do to further enhance the results, we also implement a post-processing. So the GNN might do some misclassification, minor misclassification in this case. And because we know some properties of the restore and the perturb block, we can further analyze the predictions and eliminate some misclassification. And with our employed post-processing, we are able actually to achieve 100% accuracy in identifying the perturb, restore, and original block in all of our evaluated designs. So this GNN unlock that I have just presented was a specific application. It is specifically an attack on logic locking, and it's specifically attacking this provably secure logic locking. However, when we implemented GNN unlock, the observation is that the GNN was able to identify a subcircuit with some specific properties, which means that we can generalize this and we can implement a functional reverse engineering platform using a GNN. So what is functional reverse engineering? In reverse engineering, the flow typically is that you would start with a chip and you would depackage it and then perform an iterative procedure in which you delayer and image the layer and so on and so forth. And then you analyze these extracted images, you stitch them together and extract some gate information. So at the end, you will end up with a reverse engineered gate level netlist. And this is the part that we are interested in. Now, getting this reverse engineered gate level netlist, this will be a sea of gates. It is a flattened netlist. It means there's no hierarchical information. It is difficult by looking at the netlist to infer what type of subcircuits exist in it and what is the functionality it is implementing. And figuring out these high-level components in a circuit is what we call functional reverse engineering, which is what we are specifically interested in. So we propose a GNN-based platform to do this functional reverse engineering for us. And the GNN will be able to identify for us the type of subcircuits, as you can see here, some combinational logic, and also some sequential logic. One important note to mention, this reverse engineered gate level netlist, we don't have just to get it from the fabricated chip, but we can also obtain it from the layout information during fabrication. Now, this functional reverse engineering can have good and bad intentions. Good intentions, it means that this can be used once you are able to analyze what's inside the circuit. You can identify some malicious logic. You can also verify the implementation of the circuit, ensure that it is implementing what it is supposed to implement. But there are also some malicious intent, which might be similar to our GNN unlock attack, where we were looking for a specific functionality that we wanted to remove from the circuit. Now, in GNN RE, we follow a similar analysis that is done in GNN unlock. We take the reverse engineered netlist, we represent it as a graph, we extract features for the nodes, and then we pass it to our trained GNN model. But here the GNN is trained on a large data set of different circuits that contain different components like subtractors, adder, multiplier, comparators, control block, and also some sequential elements like shift registers, counters, FSMs. And then after passing this graph to the GNN will tell us specifically the subcircuit each node belongs to in the graph. So here the GNN, what it did is that it automatically figured out the type of subcircuits, but it also automatically identified the boundaries between those. So we did not have to do any prior partitioning to the circuit before feeding it to the GNN. The GNN was able to do this partitioning for us. So this GNN RE platform is a generic platform that can be used and tailored for different applications. So now I am done with discussing the node level applications that we have implemented, and I am going to discuss the graph level. So for the graph level, we implemented Omla, an Oracle-less machine learning-based attack on traditional logic locking. If you recall, I showed this example earlier, and I showed that there is vulnerability in traditional logic locking, that there is a mapping between the added key gate and the correct key bit value, and that we typically perform resynthesis to break this mapping. I also showed you that SAIL attack was able to break traditional logic locking, but it had to perform feature engineering to encode the subcircuit, and it had to undo the synthesis. And after undoing the synthesis and moving to the stage here, the attacker would try to predict the secret key. However, one observation is that you do not have to undo the synthesis. Here, these local transformations that happened in synthesis that are surrounding the key gate, they do capture the secret key bit value. So what we can simply do, we can take a locality around the key gate and we can represent it as a graph, encode it, feed it to a machine learning model, and the machine learning model will be able to predict the key bit value based on the information it extracted from this locality. So to do this, considering this example now, we have this key gate, we extract this locality around it, so we don't consider the entire circuit. We only consider a subgraph, a subcircuit around the key gate, because only this subcircuit will be capturing the information about the key. So we take this extracted subcircuit, we convert it to a graph, and in Omla, we consider the two-hop neighborhood of the key gate, which means that here I am showing you an example of what does a hop mean. A hop, it means just one connection away from the key gate. So one hop, it means one connection. Two hops, it means two connections. So here in this example, we are able to fully represent this subcircuit in the graph. After converting the circuit into a graph, we also perform some feature extraction. And in the case of Omla, the only feature we extract is just the type of the gate itself. So for example, here I am showing you the feature vector of this node. This is actually representing this inverter. And you can see that in the feature vector, we put 1 for the entry of the inverter. Because we also only represent the gates in the graph, we also include the input-output information, the primary input, primary output information in the feature vector. So this, for example, inverter is connected to a primary output, so we put 1 in the entry of the primary output. Now, in addition to the feature vector, in this case, in Omla, again, we are interested in performing a graph level or subgraph level classification. So the GNN will be looking at the entire subgraph. We want the GNN to still be able to identify the key gate, because the key gate, it's a unique gate in this subgraph. So that's why, in addition to the feature vector that captures the Boolean functionality, we also perform some structural labeling. We specifically label the key gate using the zero a label, so only the key gate will get the zero label. And then we also capture information regarding the fan in and the fan out of this key gate. So using this sign, we are able to tell if these nodes are feeding the key gate or if they are fed by the key gate. So we observe that this is enhances the performance of the GNN, specifically because we are representing the circuit as a non-directed graph. So by adding this structural information, we're still able to capture some sense of the direction in the graph. So this will be fed to the GNN. The GNN again will generate an embedding for each node. But now, since we're interested in the subgraph level, these generated embeddings will be combined together using a readout function. So we will get just one final subgraph embedding, which will be used for the classification. And the label here, the classification label, is the key value. So this attack is able to outperform all existing machine learning-based attacks on traditional logic locking. And you can scan here the code if you want to have full access to the paper. Now I'm going to move to the discussion of the link level tasks. So you have seen now two different ways to implement logic locking. You saw the provably secure logic locking, you saw the XOR XNOR locking, and one observation we made about XOR XNOR locking is that it leaks the secret key, right? This key gate itself holds information about the secret key. So one way to solve this is to use MUX structures for locking. So the MUX in this case will act as a key gate. Here on the left, you can see an original netlist, and here you can see us locking it using a MUX. We added a 2-to-1 MUX. This MUX takes a true wire from the circuit and a false wire from somewhere else from the circuit. And the key input now will act as the select line for this MUX. Upon applying the correct key, the true connection should pass to the output of the MUX, maintaining the original functionality of the design. So here, there's no key leakage because the MUX itself does not capture information about the key. The true wire could be connected to the second or to the first input of the MUX. However, we were able to identify a critical vulnerability in Maxbased locking, which is link formation, and we proposed untangle, unlocking, routing, and logic obfuscation using GNN-based link prediction. So the way we try to figure out the true connection of the MUX, we represent the circuit as a graph, and then we keep all the connections that are non-obfuscated. So by non-obfuscated, I mean that all of the connections that are not feeding these locking muxes. So for example, the connection between gate G1 and gate G3 is visible to the attacker. It's not obfuscated. It's only the inputs to the muxes that are obfuscated. So what we do is we keep all the connections that the attacker can see and only remove the connections that are obfuscated, which are the inputs to the muxes. So here we represent them as target links. By target links, it means that we need to figure out which one of these links is supposed to be added in the network. And we solve this task using a link prediction platform. So the link prediction problem, it means giving an incomplete network, and the incomplete network for us means all the gates outside these muxes and all the connections among them, predict whether two nodes are likely to have a link or not. So the two nodes for us will be the gate that is connecting its output to the input of the MUX and the gate that is connected to the output of the MUX. So we need to figure out if these are likely to have a link or not. And we solve this task again using graph neural network. So to solve link prediction using graph neural network, we use the SEAL platform. And in here, if we have this graph and we're trying to figure out if nodes A and B and nodes C and D are connected to each other, what we do is we extract a subgraph around this target link, so basically the target nodes, and then we perform, of course, some feature extraction and some structural labeling as well, feed it to the GNN, and this GNN, of course, will be trained to perform link prediction, and it will tell us if there's supposed to be link or not. So using this, we are able to break some state-of-the-art logic locking techniques that were unbroken by any other attack. So just to give you a feel of how powerful this untangle is, we were able to break interlock. So this was the state-of-the-art logic locking scheme that we were able to break, and random mux-based locking. So both of these use muxes for locking, and Untangle is able to decipher up to 100% and 99.61% of the key bits respectively, with a precision up to 100%. We are achieving this precision of 100% only by relying on the structure of the design. Again, all of the attacks we have developed, they were considering the Oracle-less threat model, which means that only by analyzing the structure, we are able to break logic locking. So now we have reached the conclusion for today. So the advancements in machine learning and the increasing complexity of EDA tasks has led to more interest in employing machine learning to solve some different critical EDA tasks. And since circuits can be represented naturally as graphs, graph representation learning is very promising to be used. Today, we showed you how we were able to use this graph representation learning, specifically graph neural networks, to solve many interesting hardware security related tasks. And as you can see, since I am interested in hardware security, I have been using GNN for the hardware security, but some direction that we are interested in pursuing is actually the security of the GNN. So we are using this GNN for different critical hardware security applications. We need to ensure the reliability of the GNN. So this is a list of some related publications. So these publications in which we use machine learning and GNNs. Also, all our platforms are open sourced. So using these two links, you should be able to access all of our codes, all of our circuit to graph conversion, feature extraction, and so on. And of course, before we end this talk, I would like to thank my advisors and my collaborators, my postdoctoral advisor and my PhD advisor, Professor Ozgur Sinan Oglu. Some of what I presented today was part of my PhD. I would like to thank my PhD advisors from Khalifa University, Dr. Hani Saleh, Dr. Bakr Mohammed, Professor Mahmoud Al-Khutairi, and again, Professor Ozgur Sinan Oglu from New York University, Abu Dhabi. I would like to thank my collaborators, of course, my second advisor, Professor Muhammad Shafiq, Dr. Satwik Patnaik, Dr. Johan Mitchell, Dr. Abrajit Gupta, Muhammad Abdullah Hanif, and Faik Khalid. Big thanks to all my NYU and NYUAD colleagues, and thank you again for attending. I'll be happy to take any of your questions.
Okay, thanks a lot, Lilas. And now I would like to ask whoever has questions, so can write it in the chat window, how to say in the YouTube. So we have already one question from Paul. Paul is asking, do you have an idea how logic locking, how logic locking be improved to be improved with GNN resistant?
Yes, definitely. So yeah, one thing that you have observed today is that I have presented mainly GNN-based attacks on logic locking. And using the GNN, we're able to identify some critical vulnerabilities. And I believe that now, knowing these critical vulnerabilities, one will be able to implement logic locking in a way to avoid this prediction by the GNN. For example, using some explainability approach, one will be able to analyze the predictions of the GNN, understand why was it able to predict what it was able to predict, and based on this extracted information can definitely be able to implement logic locking that is resilient. So it is also definitely a topic, the research topic that we are interested in.
Sounds great. I have actually a question regarding the GNN unlocking. You mentioned that you have done two different technologies, like the 45 and I think the 65. So, in general, despite the results and the investigation, what do you think the role that the library or the technology itself could play in this context?
Yeah, definitely. So the GNN, at the end of the day, what it's capturing the structure and the connectivity in this graph. And the connectivity also includes the type of gates. So basically the composition of gates that you can see. Depending on the cells you have used using synthesis and the generated synthesized netlist, you might end up with different combinations of circuits that exist. So that will definitely affect, what sort of subcircuits you might be able to identify. If there are no restrictions, if, for example, in our analysis, we used the 45, 65, and we did not put any restrictions, like use specific type of cells, we observed a similar performance because the synthesis tool had the same task, right? Do optimization, meet timing, optimize area, and it ended up using similar types of functionalities, similar types of cells. So in that case, we did not really observe a difference.
Okay, I see. That makes sense. We have another question. Did you observe differences between benchmarks? In other words, maybe some circuits more challenging or some benchmark more challenging than others?
This is an interesting question. So in my work, I've mostly focused on the ITC benchmarks, and the ITC benchmarks, they do have similar properties. So if we're able to break one of the ITC benchmarks, it was also easy to break others. However, I did observe one thing when we were attacking using GNN unlock. GNN unlock it tries to identify this restore logic, right? And in the specific scheme, anti-SAT, I'm not sure if you're aware with anti-SAT, this restore block is implemented in an AND tree structure. So one thing we have observed is that if the original design itself has like several number of these AND tree structures, it might be confusing for the GNN to separate the restore block we're interested in from the other AND tree structures that are available in the design. So that is one observation that I have made. Also, one thing for sure is that when you use different benchmarks, the size of the graph will be different. So even for ITC itself, like starting from B14, it is a smaller circuit compared to B17. So one thing for sure, you might observe that it might take more computations to perform the analysis on B17.
But this analysis is one-time effort. So assuming like you really want to analyze a complex, I don't know, processor error SOC with a still doable, but it just takes, let's say, long time and more computing power, or the algorithm itself or the GNN or the neural network will struggle due to the huge complexity in this case?
Okay, so I wouldn't say it would struggle per se, but something that is unique about the GNN, which is unlike traditional, let's say, DNN models, is that generally in a DNN, the complexity, the computational complexity depends on the architecture of the DNN. But what happens in the GNN, it really depends on the input, in the input graph. How many nodes are in this graph? How many edges? Because the more edges you're going to have, the more dense the graph is, the more this neighborhood aggregation that you're going to do. So it is expected that even if you have the same model, when you're running it on a more complex circuit, you might observe some different computational complexity. However, there are many ways to enhance the performance of the GNN. So it does not have to be this basic implementation that I showed you. So there are methods that can do graph sampling, layer sampling to speed up training or inference on a graph.
Okay, sounds great. Thanks. I don't see further questions. Maybe,
I have
we
one.
are done. So, Ricardo, please.
I will do. So maybe, Lilas, can you share your slides again?
Yes, sure. Yes.
So maybe if you can go to, for example, slide 15.
Yes.
No, it was before 13. This one is okay.
Before? Shall I go before?
By 13, maybe. 13. Yeah. Okay. So here on the left, the logic gates you are showing, they are not yet prepared for a CMOS implementation.
Mhm.
So how you consider this? Because we have some work here trying to optimize the number of used transistors.
Mhm.
And one way is to, when you have just one uh, fan out like here, we can merge all these cells in just one. And I
Yes.
think you can also merge the logic locking together.
Mhm.
So did you consider this or no? This
Yeah,
possibility?
yeah, so it is something, of course, we have observed. Logic locking specifically can be implemented at different levels. It can be implemented at the RTL, or it can be implemented at the gate level netlist. And we can observe two changes. One is when you perform synthesis. So synthesis on its own will perform some optimization. And then further, when you do the physical design, you will have some optimization on top. Um, the example I showed you earlier, in which we do logic locking and then we perform resynthesis to perform some optimization and hide this logic locking, this is actually for the benefit. It makes this key logic more difficult to be isolated. So that is one thing, it will be embedded into the design. And one more thing, that the key logic will not dissolve completely, because the key logic is controlled by key inputs, primary key inputs. So it's not going to be something that will dissolve completely. It will be there, and the optimization will further help to embed logic locking into the design.
Okay. I think we have some interface between our work and yours. That could be interesting to talk more.
Yeah, definitely. Would love to.
Okay. So I don't know if you Sam has more questions or somebody else.
Well, I don't see questions in the chat. I think we have
Mm.
already went through all of them, and I have also asked many questions from my side, so I'm done.
Okay. So thank you very much, all you, for attending this session today, and thanks Lila for the very nice talk, and also to Hussam to sharing the session. So I wish you a very nice weekend, and I hope to see some of you next week at Laskas. Bye bye.
Bye,
Thanks
thanks.
very much, all.